So hi everybody. For some reason I do see my screen, but okay, perfect. So won't be able to see the questions on the chat for the next 10 minutes since I'm going to be doing the presentation, but really don't hesitate to ask anything on the chat. It's going to be my pleasure. So my name is Naysan. I'm the co-founder and CEO of a startup called CANN Forecast. And what CANN Forecast does is we leverage machine learning to help municipalities for two products, actually. One of them is called IntelliSwim, and it tells beach managers, so urban beaches, if the water is going to be contaminated in the next couple of hours so they can close the beach and people won't get sick. And the other product we have is called IntelliPipes. And what IntelliPipes does is that it actually identifies the areas within a drinking water network that are at risk of bursting. And it lets the municipality know ahead of time so they can fix the pipes before they break. I'll be very happy to talk about it later. And today my talk is about human interpretable machine learning and just an application to water management, to how we do it ourselves. So let's go. So human interpretable machine learning, why? Because I know that a lot of us data scientists would like to have complex models that are more and more efficient. But there are a couple of things that I wanted to share with you. So first of all, customers can have questions. So for an application, why was my credit application denied? Or, this is another interesting paper here that you can check out on the internet. So they basically added these black and white spots on the stop sign. It's called camouflage art attack. And they were able to get a misclassification rate of 85% of the image recognition device. So instead of seeing a stop sign, the automated car was actually seeing 45 kilometers. So you can imagine how bad this is going to look if we actually have automated cars everywhere. This is another fun way that you can actually, here's the article from Goodfellow now 2015. And so what they did is that they took an image of a panda, which was properly classified by the algorithm, and they added, this is a function of the gradient, but it's basically some noise that they added to the data. And it turns out that the algorithm decided that instead of being 60% sure it was a panda, it was 99% sure it was a gibbon. And for those who don't remember what a gibbon looks like, it looks like this. So being able to fool algorithms specifically for a machine, for image classification that's very mature, it's kind of scary, because then you start to ask more serious questions, like what are you going to do if your algorithms are actually discriminating without you being aware of them by gender and race, like Facebook's ad serving algorithm did. And there's actually a new bill that's proposed in the United States. It's called the Algorithmic Accountability Act of 2019. Now it's become 2019 and 2020, and you can consult it online. So it's basically going to hold all companies, all big companies that are using AI, accountable for any bias, any sort of thing that their algorithm does without being aware of them. And so this is coming for all of us. I mean, if this passes in the US, it's coming into Canada, and we are going to have to be accountable. So how are we going to help our machine learning algorithms become interpretable? And how are we going to make sure that if we ever get audited, we can give an answer? There are a couple of options. As you will see during my talk, it's really a relatively new field, interpretable machine learning. So everything is basically working itself out as we're talking. And I will be happy to share a few papers on more complex networks and how people are trying to make them become interpretable, if you want, at the end of the talk. But let's start simple. The most simple the most simple thing that qualifies as machine learning would be a linear regression model. And people use it. FICO uses like a close cousin of the linear regression, which is the logistic regression. And they use that for credit score. And why they're using regression for credit score? Because of interpretability. But so yes, linear models are interpretable in theory, because if you have a straight line that goes here, then if you have y equals 3 times x plus something, you know that whenever you increase x by 1, then you're going to increase y by 3.1, which is fairly interpretable. But that's if you're comfortable with making fairly unreasonable assumptions. And that's that you're assuming that you have a linear relationship, that all your variables are normally distributed, a few more assumptions, and then this one here, no multi-collinearity, which means that input variables are assumed to be independent, which in real life, it usually doesn't happen. So I'm going to give you an example. So if you're doing text classification, what's the probability of seeing Trump after Donald? It's not the same as seeing Trump here and Donald somewhere else. So there are lots of things that are not independent. So that assumption in particular gets violated a lot of the time. And what happens when the features are not independent? I'm just going to give you an example for IntelliSwim, one of our products. So oversimplification of beach water quality depends on rain and sewage overflows. So the way it works, you have dry weather. Many cities, like Montreal, for instance, whenever you have dry weather, all of the sewage from housings, they go directly to the water treatment plant. When you have wet weather, though, because the water treatment plant has a limited capacity, the rain falls, and often some older cities, they have combined sewage. So there's too much rain and sewer, and then all of a sudden there is a dam that opens, and it outfalls into the river, and that contaminates the water quality. So the consequence is that these two, rain and sewer overflow, they're not independent, so the coefficients are no longer interpretable. I can for sure give you more examples here. I'm shortening this presentation a little bit because it was for a longer setting, but this is just saying that if you just use sewer and rain, if you only just use one sewer and rain to predict your water quality, you can see that the coefficient for sewer 1 is 2.6, which you would think would mean that it would be the same as in here, basically, the coefficients of sewer. But the problem is that because these two variables, sewer 1 and sewer 2, are not independent, then when you add sewer 2, sewer 1 drops in coefficient. So it doesn't mean much when you're having variables that are dependent into any sort of linear model. The coefficients really don't mean much. Proposition number 2 is to use something called surrogate models. To give you an example, so what's a surrogate model? It's a model that you're going to train on your model to approximate your model. So how it's going to work is that you're going to fit two models. You're going to train your first model to try to explain reality, and then you're going to train a second, simpler model to try to explain your first model, and then you're crossing fingers that you don't have too much of an error here, because here you can understand what's going on. But there is a big problem with surrogate models. Just put it in here. So if you have a black box model that you can approximate by a simple surrogate model like a decision tree, then in reality, what it means is that your problem wasn't as complicated as you thought in the first place, and you should have used a decision tree. So for complex problems, surrogate models are not going to be the solution. And so because of that, there are some libraries that have been coded in the past couple of years called local surrogate models. So one of the examples is Lime. It's actually available in Python. You can just install it with pip. And here is the paper that gave birth to Lime in 2016. So this is actually an easier way to see it. So it assumes that your model is indeed complex, but there are some areas where locally your model, which would be the blue curve here, could be approximated by a straight line. So what Lime is going to do is going to approximate your model by the straight line locally, wherever it can. And it's going to give you the interpretability of a linear regression for that particular area where it was approximated. But so it does have limitations. Right now, current Python implementations of Lime don't work for a lot of models. And you have when you have nonlinearity, it's very difficult to approximate with a linear model. So you're kind of back with the same interpretability problem. Proposition number 4, which is something that we do actually, is to use Bayesian statistics. I don't have time to go into much details, but so Bayesian statistics is a parallel branch to frequentist statistics, which is what a lot of people are using mainstream. So in a frequentist statistic setting, you're going to say that your probability is your long-term frequency of having an event happening. So when you're flipping a coin, you flip the coin for long enough, then you're probably going to have a certain frequency of heads and frequency of tails, and there you go. There you have your probabilities of heads and tails. But there are things like NASA, for instance, when they send someone into space, they can't do long-term runs of sending shuttles into space because it costs a lot. So you've got to come with another definition of probability. And that was given to us a couple of 100 years ago by a guy called Thomas Bayes, which says that probability is a quantification of a belief. So you're going to add it's called a prior. You're going to add a belief that your event occurred, and then you're going to start working. So for those who are more technical, most AI machine learning techniques are trying to maximize something like the likelihood, and Bayesian probability adds a prior, and that's what we're using at CANN forecast. So we do work with AI models and deep learning. We work with the Montreal Institute of Learning Algorithms. But then what we do is we also ask our customers for their domain expertise and belief in, for instance, the reasons why pipes break or the reasons why water quality is bad. And then we've been working with two very good professors, to break down that complex deep learning algorithm into something that's tractable and interpretable in a Bayesian setting. I'll be more happy to give you more details at the end of the talk. But it's not, as anything, it has limitations too. You still need to make assumptions on how the model works. And in exchange for being more interpretable, Bayesian statistics, it requires your team to have a stronger math and stats background, because then the models, you have to work them yourself mainly. And it's not everybody who likes to do that and everybody who has the skills to do that. So it becomes more difficult as a startup to hire the right people. So the point of my last 15 to 20 minutes really is that it's coming for us. So there is legislation that's probably going to force a lot of people working on complex models to make them explainable. And, people have been quoting the British statistician George Box for a while. So he basically said that essentially all models are wrong, but some are useful. But it's getting harder and harder to get away with this in a situation where people are going to complain about the fact that maybe there was bias in the algorithms. And you can say, well, it's useful 99% of the time, so too bad for you if you had experienced bias. So we're going to have to make our models interpretable. But what I was trying to show you really through all these slides is that interpretable machine learning is still a new area. You see, everything I showed you had limitations, and there is a lot of work left for us to do. Thank you. All right, so here's the end of my talk. If you had any questions, feel free to ask them, and I'm gonna wait a couple of minutes. All right, doesn't seem like there's a lot of questions. Regardless, you can follow me on. No, you just add me on LinkedIn. I'll be happy to talk to you. So thanks so much for your time. And oh, I got a question. How are the insights obtained by model conveyed by the people local government? Oh, that's actually an interesting question. Thanks, Abhishek. So I'll give you an example of the insights. They're actually quite good. So we were developing a model for when the water mains break and given temperature, and we were trying to add temperature to the model. And we actually talked to a couple of engineers from one of the cities we've been working with, and they explained to us that they've been seeing every time that the water temperature at the water intake plant drops below 4 degrees Celsius, they experience breaks. And they just know that. So what we decided to do is first to do if it's true. And we checked with the historical data, and we saw that effectively there is something of a drop of temperature around fall that causes some water mains to break. And then what you can do is that you can decide that you're going to change your prior distribution, if you wish, of when the water main breaks towards that specific time and specific drop in temperature. So you're basically using their domain expertise over here to add into this distribution over here. So the data is going to be here added, so evidence from your data set. You're going to slightly tweak the evidence from your data set with the actual belief of your customers, if it makes sense. And usually what it does is that it's going to make your provisions more, I would say more accurate, even if sometimes the data was not able to capture that thing. Hope that was good enough. Well, thank you so much. All right, so have a great day, everybody, and feel free to add me on LinkedIn. We can chat. Bye bye.